Hi everyone, good morning, and we are back into our session. This is going to be lecture number 11 on random variable. Okay, so we are discussing random variable, and we are also talking about discrete random variable, and we have discussed about various things related to random variable. Okay, we have talked about probability mass function. We have talked about various things. I believe everybody might have understood the Bernoulli, distribution, Bernoulli random variable. Okay, some simplest kind of random variable we have discussed. Okay, and also we discuss about one of the very important kind of distribution, that is nothing but Poisson distribution, right? So when binomial distribution fails, okay, we go for Poisson distribution. So I will give you a brief recap about Poisson distribution in more detail. Okay, and then we will start talking about expectation, right? That is important, right? Expectation, variance, and all those things. And then we will move to continuous random variable, and that is important for your exam. Okay, so I believe next few lectures we will wind up this probability theory. Okay, so let us move ahead. So guys, this is let me move to our favorite screen. Okay, so this is gonna be lecture number 11. Outside it's raining in Mumbai, and I'm teaching you probability. So this is a great coincidence, you can say, yeah. So just want to discuss again the Poisson intuition basically, and Poisson distribution, you can say. Okay, Poisson distribution. In the last session, just I gave you a kind of a feel that, if number of, you can say trials are more, and the probability of getting success is pretty less. Okay, there we use Poisson distribution, right? So can you give me some real life example, because I just want to find the real life example, and if I give you one real life example, you can relate it. Okay, so those who are staying in, I mean, good cities, like those who have been into metro cities like Bangalore, Mumbai, or New Delhi, or any big city, rather than staying in their village. Okay, I think they might have experienced when they try to book the Ola cab, or Uber cab, or whatever. When they try to book it. Okay, so what happens, like in Bangalore, most of the time I have experienced, right? Not in Mumbai. In Mumbai, once you book it, you get the ride immediately, because here the crowd is there. But in Bangalore, crowd is there, but the thing is, they do not accept the ride. Okay, so let's say, in 1 minute, how many customers might be trying? Okay, how many customers might be trying to book the cab? Okay, you can imagine. Okay, in 1 minute, right? Okay, so if you're going to consider the binomial distribution, so you can say that in 1 minute there are 60 seconds, right? So there might be a 60 trial, right? But we are ignoring the fact that within 1 second also many customer might be trying, to book the cab. Understand? So at that point of time, binomial distribution cannot capture the situation. Okay, the Poisson distribution might capture it. I believe this is fine, and everybody can relate with this example. Okay, so the example what I'm trying to convey here is, the example that I just want to give you is the ride sharing application. Okay, so ride sharing application, you can say, ride sharing application. Okay, that is nothing but you name any Uber or whatever, right? Or Ola in India, right? So you might experience this Poisson distribution over there, right? So please do remember this. ठीक है, आपको पॉइजन इंट्यूशन इस तरह कहीं नहीं मिलने वाला है, द वे आई एम टेलिंग यू, एंड यू विल नेवर फॉरगेट इट. ओके, दिस इज काइंड ऑफ पॉइजन इंट्यूशन, यू कैन से. So just going to explain you. Okay, so this is the Poisson, I'm just going to show you quickly. I'm not going to write anything, just you see this. So what we can do here is, I'm just going to explain you the Poisson intuition. Okay, what is the intuition behind this Poisson distribution, right? So in this section, we saw that so the intuition behind the Poisson derivation, right? Okay, that probability mass function that you got, okay, and simply you are mugging up as a formula. So I don't want you to mug up as a formula. Just find it intuitive, okay? It is both great way to deeply understand the Poisson as well as a good practice with the binomial distribution, right? So let's look at let's work on the problem of predicting the chance of the given number of events. Okay, given number of events occurring in a fixed time interval, right? So suppose there is a fixed time interval. You can say that 1 minute, 1 hour, whatever. So I'm just going to consider 1 minute only, right? So in 1 minute, okay, number of events going to occur. And if I take one particular example, right? अगर मैं एक particular example लेकर आपको समझाता हूँ, then your life, you are going to accept this, you're going to capture this concept very easily, right? Okay. So देखो यहाँ पर आपको करना क्या है कि you have to observe, right, the number of events occurring in a fixed time interval, right? Okay, the next minute, for example, you can say that imagine you are working on a ride sharing application, right? Okay, so you are a customer, but suppose you are a, you can say that you are a cab driver, right? Okay, let's say I'm a cab driver, and I'm working on a ride sharing application, and we care about what the probability of how many requests we get from a particular area. Okay, let's say let's say let us be a cab driver at this moment. Forget about engineering rule and everything, right? So in particular areas, let's say you are in Belandur, right? In Bangalore, one place is there, Belandur, right? So or you can consider your place as well. Let's say I'm in Mumbai, okay, and I'm nearby Marine Drive, okay, or you can say, let's say I'm nearby any any airport like Chhatrapati Shivaji Airport in Mumbai, okay. So and I'm working on a ride sharing application, right? So what we care about is the probability of how many requests, okay, how many requests you get from a particular area, right? So from historical data, like certainly we will be having a historical data, right? Some data might be there. Accordingly, we are going to use the that app and work in that area only, where the probability is high that we will be getting the number of requests, okay, in certain time interval. So from historical data, you know that the average request per minute, this is the time rate, okay. Last time, I think in the last session, I told you also, okay, if you are not able to understand lambda, then you can forget about it, right? Next time I will explain you. So this average request per minute, okay, this is nothing but a rate, okay, kind of time rate, you can say, is lambda equal to 5. Okay, so in 1 minute, okay, how many requests you are getting, that is nothing but here lambda equal to 5. What is the probability of getting 1 2 3 requests in a minute? That is a question. So average is given, okay, average request per minute is lambda equal to 5. Now the question is, what is the probability of getting 1 2 3 requests in a minute? Okay, that is a question. Okay, so this kind of problem we can solve using Poisson, right? But let us try to approximate a solution to this problem by using binomial distribution, right? So just going to use the binomial distribution. Okay, this is just a like we are trying to break our head. Okay, we are just using binomial distribution, though binomial distribution is going to fail. Okay, it cannot capture each and every second. Okay, understand? So you know that as the number of trials become more and more, okay, so, and the probability of getting you can say probability of getting a request is gonna be pretty less, okay, in that, understand? So what is the meaning of probability of getting success? Probability of getting success means you get the request and you're going to accept it also, okay. So many requests will be coming, understand? So I think you might experience, right? So in Bangalore I have experienced many times. ठीक है, मैं आपको बता रहा हूँ कि suppose we are booking a cab Okay, so driver, when we go to nearby the auto or cab, right? So driver is there, he knows that. Okay, particularly auto cab, right? So, you know, we are looking at them, right? So they are not accepting it, and they are getting, you can say, many requests in that particular interval of time. Okay, आई थिंक दिस इज क्लियर. ठीक है, सो ये आपको याद रखना है. ठीक है, कि फ्रॉम द हिस्टोरिकल डेटा यू नो दैट द एवरेज रिक्वेस्ट per minute is lambda equal to 5. What is the probability of getting 1 2 3? Okay, so let me give you one particular example. I mean, just going to approximate this situation, you know, this solution with the help of binomial distribution. ठीक है, so we could approximate a solution to this problem, okay, by using binomial distribution. Let's say we split our 1 minute, you can say 1 minute into 60 seconds, right? So in 1 minute there are 60 slot, you can say, right? I'm not going to consider 0.99 seconds. I'm just going to consider 1 second, 2 second, like that. Okay, so there will be 60 second in 1 minute. Yeah, so there is 60 second in 1 minute, and make each second as an indicator Bernoulli random variable. Okay, indicator Bernoulli random variable means you either get request or you don't get request. Okay, Bernoulli can give you, you know, binary situation always. Remember, Bernoulli will always give you, you know, either you get success or failure. Understand? So either you get request in that particular time interval or you don't get request. Okay, so if you get a request in a second, let's say, okay, if you get a request in a second, like in Mumbai, people get request in a second, right? Lot of crowd, huge crowd is there, right? But in Bangalore also the similar story. So if you get a request and there is a particular time interval, okay, like in the evening when the offices, you know, many people leave their office, at that time they book it. So if you get a request in a second, then the indicator is 1, indicator random variable is going to take 1, right? Otherwise it is going to be 0. So here is a visualization of our 60 binary indicators, you can say, right? So in this example, imagine we have the request at 2.75 second, 2.75 second, okay, and 7.12 second. The corresponding indicator value variables are nothing but what? Blue fixed line, right? So I'm just going to show you this. Okay, देखो. So what I have done here is I have divided entire 1 minute into 60 second, and this is nothing but, you can say, 2.75, okay, and this is nothing but 7.12. Okay, so I'm just going to, I'm just approximating, the solution using binomial distribution. हालांकि यहाँ पर आपको पॉइजन यूज करने में ज़्यादा अच्छा रहेगा, है ना, ज़्यादा अच्छा रहेगा, क्योंकि इन 1 second you might get n number of requests, okay, you don't know, and as n tending to infinite, okay, so many requests you are getting, understand? So but here what we are doing is we are just seeing in particular interval how many requests you are going to get, how many events are occurring, right? तो ये आपको समझना है, ठीक है? So the total number of requests, okay, next what we can do here is the total number of requests received over a minute, okay, can be approximated as a sum of 60 indicator random variables, okay, like x equal to 1, okay, which conveniently matches the description of a binomial, okay, understand? So if you take you can say that each indicator as like the Bernoulli random variable, and if you're going to add them, see, in 1 minute there will be 60 indicator random variables, and if we are going to add them, sum them up, right, so we are going to get the binomial distribution, right? A sum of Bernoullis. Binomial is nothing but what? Binomial is nothing but sum of Bernoullis, okay? So you specifically define x be the number of requests, okay, in a minute, you can say number of requests in a minute, and capital X is nothing but a binomial, okay, and how many requests you're going to get in 1 minute, guys? 60 requests, you can say, right? I mean, I'm not going to consider between 1 to 2 second, between 1 to 2 or 2 to 3, and we are just getting what we are observing how many requests we are getting in 1 minute. ठीक है, ये हम अप्रोक्सीमेट कर रहे हैं बायनॉमियल से, तो ठीक है। अगर हम पॉइजन की बात करेंगे तो फिर हमें ऑब्जर्व करना है 1 to 2 में भी तो यू कैन गेट नंबर ऑफ रिक्वेस्ट, राइट। सो हियर n is going to be infinite, okay। here we are just considering the integer values, understand? integer number of times, okay। so what is the probability p of success on single trial, you can say, okay, to make the expectation, okay। so I will talk about what is this expectation meaning. Expectation is nothing but the average, you can say, okay। so to make the expectation of x equal to the observed historical average lambda equal to 5, we should choose p so that lambda is nothing but what, lambda is nothing but expectation of x only, right। so in case of binomial distribution, you know, we are trying to take expectation as lambda. In case of Poisson distribution, we know that lambda is nothing but the expectation only or the variance also, right। सब कुछ सेम ही होता है, बट बाइनॉमियल केस में थोड़ा सा डिफरेंट है, मतलब आपका जो एक्सपेक्टेशन और वेरिएंस रहेगा दोनों डिफरेंट आएंगे, ठीक है। सो व्हाट वी कैन डू हियर इज सो फ्रॉम द हिस्टोरिकल एवरेज एक्सपेक्टेशन मैचेस द हिस्टोरिकल एवरेज, ठीक है। लैम्डा इज इक्वल टू एक्सपेक्टेशन ऑफ एक्स का मतलब क्या है, द एक्सपेक्टेशन मैचेस द हिस्टोरिकल एवरेज and this is nothing but the expectation of the binomial random variable np, okay, this is np, okay, binomial distribution, okay। so I will prove also how you have got the expectation of the binomial distribution as n times p, okay। n is nothing but the number of trials and p is nothing but the probability of getting success, ठीक है। ये फॉर्मूला है, इसको मैं प्रूव करूंगा जब मैं एक्सपेक्टेशन आपको डिटेल में पढ़ाऊंगा। And so from here you can compute p, and p is nothing but the probability, right, okay। so p is gonna be lambda by n, okay, that is solving for p, right, understand। so let us take some value here, some value we are going to take, right। so you can take some value, right, some value you can take here, okay, just to realize, okay। so in this case lambda equal to 5 you take and n equal to 60 in 1 minute 60 trials, okay। so probability is gonna be what guys, 5 by 60। so if you try to approximate with the help of binomial distribution, so bin n equal to 60 and p, so you need only two parameters in case of binomial you know, random variable binomial distribution, right, n equal to 60, n and p only, right। now we have a form for x, okay। we can answer the probability question about number of requests using the binomial PMF. so this is the formula, I think everybody can recall, right। this is nothing but your probability mass function formula, right, okay। and here x is nothing but the number of success that you have to observe, right। what is the probability of getting one request, okay, two requests, three requests, right। समझ आया ना, तो आप फॉर्मूला आप कर सकते हो, right। so let me take some example, okay। as you can see number of trials are more guys, right, so we can't get exact, okay, we are going to approximate। so you see here this is the situation, okay। so suppose we are trying to find the probability of getting one request, okay, out of 60 trial, okay, like out of 60 like what is you know, 60 is nothing but number of trials in 1 minute, okay, we can get 60, but we are getting the request 1, right, in 60 out of 60, okay। so this is the formula, understand, I mean in the formula we can plug all those values, right। so 60 c1, okay, so probability is going to be 0.0295, probability of getting, you know, probability of getting success 2 times out of 60 is nothing but 0.0790, and 3 times you see 0.1389, I think you are able to relate, okay, ठीक है। we got the answer, right, but what we have forgotten here is this is just an approximation, guys, you don't have to forget this is the approximation, okay। we have approximated things, हमने क्या किया है कि हमने 1 मिनट को 60 सेकंड में डिवाइड कर दिया है, we don't care about what is happening between 1 and 2 second, right, 1.5 सेकंड में क्या हो रहा है, we don't care about that, right? So number of trials are fixed here, 60 trials are there, right? But as you are going to care about what between each second as well, how many, you know, how many requests you are getting, then number of trials are going to be huge, right? And can become infinite, okay? So this is one of the great intuition that I wanted to give today, right? Poison intuition. This is called poison intuition. So you just suppose you don't understand anything out of the class, you just take one A4 sheet paper and think about yourself. Suppose you are a cab driver, right? And in you and you are worried about getting requests, right? So you will certainly choose some area where you are going to you are likely to get many requests, right? So you will think also, okay, suppose let's say I'm going to start my journey now, right? So you will be standing in one place inside the car, and in some minute, like let's say 1 minute, how many requests you're gonna get, right? So you can think about it, okay. And if you're going to approximate in 1 minute, so 60 trials. But guys, go for poison, okay? Understand, poison distribution is, in this situation, poison is very important, understand? So don't go for this, right? So don't forget, this was just an approximation, right? So okay. So what you have to do here is you have to divide. Dekho. So great, but don't forget, this was an approximation, and we did not account for the fact that there can be more than one event in single second, guys. In 1 second there can be more event, okay? So one way to use this issue is to divide 1 minute into more finer, you can say fine grained interval, okay? The choice is to split it into 60 second was rather arbitrary, right? I mean, ठीक है, आपने 1 मिनट को 60 सेकंड में डिवाइड किया, राइट? बट let's divide 1 minute into 600 DC second, and again with the request 2.75 and 7.12, right? So let me show you that picture also, ठीक है? देखो, आपने 600 कर दिया है, क्या कर दिया? 600. See, this is the situation. In 1 minute you are going to divide this, ये देखो 600 times, okay? 600 DC second में डिवाइड किया, means you are going to get 600 requests, okay, in 1 minute, okay? So can we go for approximation again? So whether binomial distribution will work here? So you will say yes sir, let me compute, okay? So though I don't allow people in the exam to do all these things, just to get you feel, okay, I'm just explaining all these things, okay? So now number of trials are what? Number of trials are 600, and the probability is nothing but 5 by 600. Dekho, as long as the number of trials are more and more and more, right? Okay, and we have considered from the historical data the average request per minute was 5, okay? Average request per minute, lambda was 5. So here we have computed, and what we are trying to do here is we are comparing with the binomial distribution, right? So lambda is equated to the expectation of the binomial distribution, or you can say Bernoulli trials का जो था, ठीक है? Some of the Bernoulli trials, and then we are getting here x now. So probability 5 by 600. So as I told you, as the number of trials becomes more, the probability of getting success is gonna be less only, right? So you see p is going to be pi by 600, right? So your denominator is increasing, understand? So you see how complicated it is going to be, okay? In fact your online calculator will also be failing to solve this, okay? ठीक है, तो आप देखो यहाँ पर कैलकुलेशन क्या है, ठीक है? So here the x is going to be what? N equal to 600, p equal to 6 by 600. So we can repeat our example calculation using better approximation. ये सब approximated values हैं, ठीक है? So till now you had just a formula, right? But now I think with the example of RIDE, working on RIDE application, right? So now you may be understanding, yes, this is the poison intuition. Now we need Poisson intuition. Okay, so you choose any value n. Okay, understood. So number of buckets to divide are 1 minute into what? You see here, this is important. You see this. अब आप क्या कर सकते हो? You can divide, subdivide these things into more finer. Okay. These intervals are going to be very close to each other. Understand? So the life is this. This is the. My question is gonna be final question. Is this? The larger the n, the more accurate the approximation is. So what happens when n is infinity? It becomes the Poisson. And I think you guys can recall now, the Poisson is nothing but what? Sorry, here capital X. X is going to be k, which is nothing but lambda to the power k. Okay, lambda to the power, I think this is the form, yeah, e to the power minus lambda, lambda to the power k, k factorial. This was the formula only, na? This was just an approximation, you can say, yeah. Yes, lambda to the power k, e to the power minus lambda, lambda to the power k, and this. Okay, so I'm just going to explain you how we get the derivation of the Poisson, right? Okay, so Poisson as a, you can say, binomial in a limit. Okay, Poisson is nothing but what? Poisson is nothing but a binomial in the limit. Okay, because we are doing what? N tending to infinite. Number of trials are becoming pretty large, right? So this is the formula for PMF. So what is Poisson, guys? Remember that Poisson is nothing but Poisson, you can say a binomial in the limit. Okay, ठीक है. तो जब भी पॉइजन की बात आएगी ना, तो यू कैन ऑलवेज रिकॉल, राइट, यू आर अ कैब ड्राइवर एंड यू आर यूजिंग द राइट एप्लीकेशन. ठीक है. So I think this is clear, right? So let me derive this formula, and I'm not going to, you can say that, show you everything, right? So okay, so we can divide 1 minute into infinitely small buckets, you can say. बहुत छोटे छोटे buckets में. तो आप ऐसा बोल सकते हो कि, you see, this is the situation now. So what we are doing here is we are dividing. You see this, very small. We are not able to see, in fact. Okay, ऐसा लग रहा ना continuous हो गया है. See, we have divided, we have chopped off, you can say, right? 1 minute into n tending to infinity, right? Earlier it was, we were able to see the buckets, right? Fine. So let me derive, and I'm not going to give you the, kind of, okay, so just I'm going to show you this derivation part. Okay, 1 minute. Though you don't need these derivations, but yeah, fine, you can just follow it. Okay, so yeah, you see, guys, this is the derivation. So I think you all might be able to see this. Okay, so let me go through this. What is this? So derivation of the Poisson. Okay, what does the PMF of X look like now? We have infinite division of R 1 minute, right? So we can write the equation. Think of it as n goes to infinity, and recall P is still equal to lambda by n, right? So lambda is nothing but the average number of requests, from the historical data. So this is the this is what the binomial distribution, as we know. Okay, and we are just applying the limit. Okay, so Poisson is what? Poisson is nothing but the binomial distribution only, but there will be a limit n tending to infinite. Number of trials are going to be more. Yeah. So while it may look intimidating, the expression simplifies nicely. This proof uses a few special limits rule. Okay, तो ये चीज आपको याद रखना, that we haven't introduced in this, you can say, ठीक है. Okay, So yeah, so you see guys, this is nothing but a probability x equal to small x. Now start with the binomial. This is the first step. Then you have to expanding the power terms, right? You have to expand the power terms. So what you can do here is, यहाँ पर आप ऐसा कर सकते, जैसे a by b है ना, मान लो n है, तो इसको लिख सकते हो a to the power n, b to the power n. Okay, understand? So I think this is clear. Or suppose this is here, the minus sign is there. Suppose somebody has given like this, so you can also write this as you know, suppose this is x, right? So a by b, you see here, अगर मान लो सेम है, ठीक है, तो आप क्या कर सकते हो, what I'm trying to convey here is a to the power m and a to the power n, so you can write this as a to the power m minus n, ठीक है. These two laws we are using. Okay, then expanding the binomial terms, so you can expand this guy also, ncx को आप कैसे लिख सकते हो, n factorial by n minus x factorial and x factorial from the formula only, right? And then you can use this rule. I think everybody is familiar with this rule from the limit. Okay, limit, ये बहुत important rule है, ठीक है. This rule is nothing but suppose limit tending to n tending to infinity. Okay, 1 minus you can say that yeah, lambda by n, okay, to the power n. So ये आ जाएगा e raised to power minus lambda by n into n, which is e raised to power minus lambda, ठीक है. ये I think many of you can recall from single variable calculus. I have taught you these things, right, from the limit. So ये डेरिवेशन समझने के लिए आपको थोड़ा सा मतलब समझना पड़ेगा. And then you can you can say that lambda by n अगर है, n tending to infinity जा रहा है, that becomes 0, right? So you can split the first term. Okay, you can split the first term, and then you see this is also very important approximation. You see n factorial by n minus x factorial is equal to n to the power x, right? And then you have to cancel n to the power x and you will get simplified this. Okay, so I think you guys can see this derivation. I need not to explain it. Okay, so this is nothing but a beautiful expression, you can say, and we can compute the probabilities, right? So now, and this is more accurate also, ठीक है, that is a conclusion. ये देखो, so this is the beautiful expression. Now we can calculate the real probability of the number of requests in a minute. Okay, so if historical average is lambda equal to 5, okay, so this is the situation, right? You can apply this formula. You can say small x e raised to power minus lambda to the power x upon x factorial. So ये आप formula use कर सकते हैं, ठीक है. And this is both accurate and much easier to compute, ठीक है. Number of requests in a minute, you can say. What is the probability? Okay. So if someone is going to ask you what is this Poisson and all, so you can describe using this example, real life example that I told you, right? Fine. So I think everybody understood this. Okay. So you can also change the time frame also, right? Okay, like, that is also important. Okay, so Poisson is amazing. Okay, Poisson is amazing. In 1 minute I'm talking about, but you can also talk about, so changing the time frame. Say you are given a rate over 1 unit of time, but you want to know the rate in another unit of time, right? For example, you may be given the rate of hits to the website per minute. Okay, ये भी एक example आप ले सकते हो. You may be given the rate of hits. Okay, suppose I launch my website. In future I'm gonna launch it, as everybody knows also, right? So I'm going to ponder, right, how many hits I'm going that website is gonna get per minute. ठीक है, you want to know the probability over 20 minute period. अभी तो हम 1 मिनट की बात कर रहे हैं, लेकिन अगर टाइम फ्रेम चेंज होता है 20 मिनट पीरियड में अगर देखना चाहते हैं, तो you just need to multiply the rate, this rate by 20 in order to go from per 1 minute of time rate, okay, to obtain per 20 minute of time rate. बस 20 से आपको मल्टीप्लाई कर देना है और कुछ नहीं करना है, ठीक है। तो अगर आपका टाइम फ्रेम चेंज होता है, ठीक है, तो आप ऐसा कर सकते हैं। सो आई थिंक नाउ योर कॉन्सेप्ट इज क्रिस्टल क्लियर, ठीक है। तो आप ऐसा सोचो, अब पूरा जितना भी मैंने आपको स्नैपशॉट इसमें डाला है पूरा गो थ्रू करो अच्छे से, इसको नोट्स बना लो। लाइफ लॉन्ग के लिए आपके लिए इससे अच्छा एक्सप्लेनेशन नहीं मिलने वाला है, ठीक है। मतलब एज फार एज द गेट एग्जामिनेशन इज कंसर्न आई एम टॉक अबाउट, ओके। हम ISC IIT की बात नहीं कर रहे, वहां जाकर आपको बहुत ज्यादा लर्निंग होने वाली है। इफ यू गो टू MIT, if you watch MIT, you're going to learn much. But this, what I'm trying to convey here is I'm teaching for GATE, right? My main objective is to help you crack GATE, but आपके पास इतना knowledge रहे कि when you are going to appear in the interviews, right? So you should be able to answer the question, right? That's what my objective always is, right? Being in Mumbai, outside it's raining and I'm explaining what the binomial distribution and uh, uh, applying the limit, okay, and we're going to get the Poisson distribution. So this is one of the amazing result, okay, as a Poisson, okay, Poisson induction. I was not able to understand when I was studying Poisson, right? Let me be very honest about it, right? But you guys are now, I think now you will appreciate about it, okay, thank you. If you are going to appreciate it. Fine, so ठीक है, तो ये चीज आप याद रखना। So this is done. Now we will come back to our important concept like expectation, ठीक है। expectation की बात मुझे करना था, okay, because expectation, so many times we have got expectation here, right? So what is this expectation or a mean of random variable? Expectation slash mean of random variable. Expectation slash mean of random variable, okay. So I'm just going to give you one kind of example here for the motivation sake, okay, so that you can understand that how we are going to get the formula out of it, okay. What is the formula for expectation mean of the random variable capital X, okay. So I will give you one sort of example, you can say, that will be just like a, to motivate this topic, right? So what is the motivation here, guys? The motivation here is nothing but let's say you are playing a game 1,000 times, okay. You can say motivating example I'm just going to take. Let's say okay, we play a game 1,000 times, okay. Let's say we play a game how many times? 1,000 times, okay. So we are going to model and we are going to gain something, we are going to gain some money as well, you can say. We are going to gain something, some money we are going to gain at each play, okay. When we are playing a game 1,000 times, we are going to get some random money. Like I think we have done also, right? Suppose I don't want to talk about any other game online, okay. So when we play online any sort of game, so we always get something, some random gain. It can be 1 rupee or 2 rupee, doesn't matter. But whenever we play game online, we get something, right? So okay, though I don't play game and all, but I'm just giving you kind of example. So we play a game 1,000 times and random gain we are going to get, okay. Random gain okay, random gain at each play, okay, we are going to get, okay. So we are going to describe this random gain at each play by the average gain, right? Okay, average gain, average is nothing but what? Average, I think average everybody knows average. Okay, so how to compute this average? I'm just going to take the help of random variable, guys. So random variable I'm just gonna choose. Okay, that is nothing but you can say that random variable x is there, right? Random variable x is there, and you're going to win the game. You can say okay, play a game 1,000 times, random gain at each play described by what? X is nothing but 1. Okay, x is going to be 1. Sorry, x is nothing but 1. X is going to be nothing but 2, and x is nothing but 4. Okay, this is a gain that you're getting. Okay, kind of, okay, random gain you're getting 1, 2, 4. Okay, and with the probability you can say that with the probability you can say that I'm just going to mention the probability here simply. Okay, you can say 1 rupee, 2 rupee, 4 rupee, ऐसा आप बोल सकते हो. ठीक है, x is 1, 2, and how many times you're going to get this 1, 2, 4, that I will tell you, right? So you are playing a game 1,000 times, you can get 1 rupee, 2 rupee, 4 rupee, ऐसा आप सोच लो. ठीक है, probability of getting 1 is nothing but 2 by 10. ठीक है, probability of getting 2 is nothing but 5 by 10, and probability of getting 4, you can say rupee or $4, is nothing but 3 by 10. ऐसा बोल दो कि 1 to 4 what they represent is kind of dollar or rupee. Okay, as a random variable. Sometimes you get $1, sometimes you get $2, sometimes you get $4, right? And how many times you're playing game? 1,000 times. If you're going to play 1,000 times, so how many times you're going to get x equal to 1? How many times you're going to get x equal to 2? How many times you're going to get x equal to 4? Right? I think you can compute now. So 2 by 10 times 1,000 का मतलब क्या है? You're going to get 200 times, right? 200 times, यहाँ आपको 500 times आ जाएगा, यहाँ आपको 300 times, right? So you're going to get, okay, you're going to get $1, or you can say 1 rupee 200 times. You're going to get 2 rupee 500 times, 5 rupee 4 rupee 300 times. Okay, so now how can you find the average gain? Average gain is going to be 1 into 200 plus 2 into 500 plus 4 into 300 upon total. Total is nothing but 1,000 only, right? Because 1,000 times we are going to play the game. Okay, so I think now you understood this via this example. Okay, ठीक है, जो मैं आपको एग्जाम्पल बताना चाहता हूँ कि अगर आप कोई गेम 1,000 बार खेलते हो तो समटाइम्स यू गेट $1, $2, $4, or 1 rupee, 2 rupee, 4 rupee, and along with certain probability, 2 by 10, 5 by 10, you know, 3 by 10, and how many times you're going to get 1, 2, x equal to 1, x equal to 2, x equal to 4. You can compute, by having by multiplying probability times the number of times you're gonna play the game. So 200, 500, 300. अब ये तो आपको पता है एवरेज कैसे निकालते हैं, काइंड ऑफ वेटेड एवरेज है ना ये. ठीक है, तो if you're going to further take a look at this average gain, so what you can do here is you can split this. So 1 by 200 upon 1,000 plus 2 into 500 by 1,000. You can write like this, right? ठीक है, 4 into 300 by 1,000, right? So now you can further cancel out something. Okay, so here ये सब cancel हो जाएगा. So you are going to get something, right? So I think, yeah. So if you look here, guys, 1 times the probability. Okay, this is 1 random variable value. The value which random variable takes is 1, and this is the corresponding probability of it. The random variable takes the value 2. This is the corresponding probability now. Random variable takes the value 4, and this is the corresponding probability. You can say this is nothing but 1 into 2 by 10 plus 2 into 5 by 10 plus 4 into 3 by 10. Okay. Okay, so instead of finding this, how many times you're going to get x equal to 1 or something, you just take 1 into the times the probability to get the average gain. And this is the motivating example, okay, to get the formula for expectation. So expectation is defined as what? What is expectation, guys? Expectation is defined as, remember, this is the definition now. Okay, I'm just going to write expectation is defined as expectation of x. Okay, this is nothing but an operator. You can say expectation operator operates on the random variable x, and you're going to get the random variable, the value the random variable takes. This small x is nothing but the value, numerical value the random variable takes, corresponding to the probability mass function, you can say. Okay, corresponding to numerical value x corresponding to probability, and you're going to add all of them, right? So if you add over all x, this is the formula for expectation. I think many of you can relate now why we are multiplying x times the probability mass function, or x times the probability, right? And we are summing them up. Since we are dealing with the discrete random variables, so we will be summing them up. Okay, we will be using this summation notation. But in case of continuous random variable, this summation will become the integration. Very simple. ठीक है, तो एक्सपेक्टेशन की डेफिनेशन बाय डेफिनेशन क्या होती है? एक्सपेक्टेशन ऑफ एक्स इज नथिंग बट the numerical value that the random variable takes, small x times the probability mass function. So आपको दिया रहेगा x, whatever value it takes, corresponding probability, multiply them, add them, you will get the expectation. So I think this is clear, right? So I believe ये आपको समझ में आ गया फॉर्मूला कैसे आता है, ठीक है? So average in large number of independent repetition of the experiment. Okay, so suppose we have got some sort of experiment and there is an independent repetition of experiment. So what is the average, right, in large number? So remember that one important caution that you have to keep in mind is this should be finite also, right? Okay, suppose you are performing experiment, right? So suppose we have got the infinite sum. Okay, so ये caution आपको हमेशा याद रखना है. This caution is very important. So it should be finite. Okay, so ये important है. Yes, this summation must be less than infinity. Okay, this is important because you might get if we have infinite sum, so you have to make sure that that series should converge, and that must be less than infinity. This is nothing but a convergence. Okay, so it needs to be well defined. Okay, so I think this is clear for all. Yeah, so let us compute expectation of the Bernoulli random variable first. Okay, expectation of Bernoulli random variable. आप बोलोगे सर ये तो बहुत सिंपल है. Yes, let us recall that what is the random variable, Bernoulli random variable? This is 1 with the probability p, 0 with the probability 1 minus p, right? So now we can apply the definition here. So expectation of x is nothing but what? Expectation of x is nothing but the value of the random variable 1 times the probability plus 0 times 1 minus p, which is nothing but p only. So you see here, one of the very good news, expectation is equal to the probability p, right? Okay, in case of Bernoulli random variable. So you don't have to compute also, you can directly say this is the expectation, okay, corresponding to the Bernoulli random variable. Okay, I think this is clear. And let's say if x is an indicator of the event, if x is an indicator random variable of an event A, right, of an event A, so you can say that x is going to be IA. Okay, so x equal to 1 if and only if A occurs, that we know, right? If events occur, then only x is gonna be 1. Okay, so what is the probability here, guys? Probability is gonna be P of A, simply P of A. Okay, So what is the expectation? Expectation of IA indicator random variable IA is gonna be P of A only. Simple. Okay. Okay, for Bernoulli random variable, I told you. Let's compute the expectation of the uniform random variable. Expectation of this uniform discrete random variable. Okay. See, I'm not talking about anything related to continuous at this moment. ठीक है, हम बात किसकी कर रहे हैं सर? एक्सपेक्टेशन ऑफ यूनिफॉर्म रैंडम वेरिएबल, डिस्क्रीट रैंडम वेरिएबल. अब आपको तो फॉर्मूला पता है तो यू कैन कंप्यूट इट, राइट? So I'm again going to recall those things, right? So just recall that uniform, मान लो ऐसा है, uniform and the random variable which takes a value, you can say that 0, 0, 1, 2 and so on till n, right? And you can just plot the PMF, right? So let me plot the PMF as well. Okay, the corresponding PMF and the probability is gonna be same for all the random variable value it takes. Okay, probability of getting x equal to 0, x equal to 1 uniform है ना, तो equally likely होने वाला है. So if there is a 0 to n, right, 0 to n, so how many values the random variable can take? Can somebody compute here? So n minus 0 plus 1, that is n plus 1, right? n plus 1, ठीक है. So यस, ऐसा रहेगा सिचुएशन, ठीक है. 0, 1, 2, 3 and so on till n. Okay, so total how many is there? If you try to find the length of it, okay, what is the length of this sequence? Length of the sequence is gonna be what? What is the length of the sequence? This is the sequence of 0 and 1 and up to n. So length of these sequence is going to be n minus 0 plus 1, which is n plus 1. So the probability is going to be what? Corresponding probability is going to be 1 by n plus 1. Okay, so that okay, I will explain you why this is how we are doing, right? Okay, as we move ahead, because the total, okay, total probability must be equal to 1, that everybody knows, right? So if you sum you know, p of x, if you sum them up, right, so that should be 1. Okay, that's why we are writing 1 by n plus 1, right? So what is the expectation now, guys? Expectation, how to compute the expectation? So expectation is going to be 0 times the probability, okay, that is 1 by n plus 1. 1 times the probability n plus 1. सब जगह तो सेम ही है ना, n times 1 by n plus 1. ठीक है, तो यहाँ से कॉमन आ जाएगा कितना? 1 by n plus 1 कॉमन. So 1 plus 2 plus n. So I think from the aptitude everybody knows that this is sum of n natural numbers, conjugative n natural numbers, which is nothing but n times n plus 1 by 2. इसको यहाँ से कैंसिल कर सकते हैं, तो n by 2. So what is the expectation of the discrete random variable, uniform discrete random variable is n by 2. ठीक है. So I've given you the proof as well. Many people will not give you the proof, but I'm just giving you the proof so that you can feel it. ठीक है, तो एक्सपेक्टेशन के क्वेश्चन आप लगाना चालू कर दीजिए. ठीक है, you guys can start applying the okay, understand? So please do remember that. Okay, please, this is important. ठीक है. नेक्स्ट इज या, मुझे ऐसा लगता है कि बहुत ही इजी है, राइट? लाइफ इज वेरी सिंपल. एंड एक्सपेक्टेशन एज अ पॉपुलेशन एवरेज भी आप सोच सकते हो, क्योंकि स्टैटिस्टिक्स में एक्सपेक्टेशन एज अ पॉपुलेशन एवरेज ही रहता है. एक्सपेक्टेशन एज अ पॉपुलेशन एवरेज. Okay, fine. So suppose there are n number of students, okay, n number of students. So you know, n number of students are going to be population only, and if I'm going to talk about a random variable, so I can say, yeah, weight of the student is a random variable here. So suppose I'm going to pick up ith student. So the weight corresponding to ith student is going to be xi, right? And we are going to pick up student at randomly. जैसे मैंने आपको पहले लेक्चर में बताया था example, okay? We pick up some we pick up some student, okay? And we have put them into the weighing machine and we got the weight of them, right? So ठीक है. But we are going to pick up any student. So if there are n number of students, what is the probability, guys? All students are equally likely, right? So the probability corresponding to each student being picked up is 1 by n. किसी को भी हम ले सकते हैं ना weight measure करने के लिए, right? So that is important. So ये कुछ points है, आप यहाँ पर देख लो, ठीक है? n students, weight of ith students, okay? Experiment pick I student at random, all equally likely. So the probability is gonna be 1 by n. And random variable x, that is nothing but the weight of selected students. Assume xi's are distinct, okay? And size of the sample space is n, okay? So that's why the probability is gonna be 1 by n. Okay? What is probability of xi, guys? This is the probability mass function. Probability of x equal to xi, which is 1 by n, right? Now if we want to compute the expectation, तो expectation formula तो same ही रहेगा. Expectation of x, okay, that is nothing but summation xi p xi, okay? So and here I, so xi is nothing but what? Xi is going to be this is 1 by n, so I'm just going to take outside, and this is nothing but sum of xi. ठीक है, ये हो जाएगा आपका एक्सपेक्टेशन एज द पॉपुलेशन एवरेज. ठीक है, सिंपल फॉर्मूला है और कुछ भी नहीं है. ठीक है, सो आई थिंक दिस इज क्लियर फॉर ऑल. एंड देयर आर सम एलिमेंट्री प्रॉपर्टीज, सम बेसिक प्रॉपर्टीज ऑफ द एक्सपेक्टेशन. ठीक है, तो आपको लेक्चर्स को अच्छे से देखना है, नोट्स अच्छे से बनाना है, बिकॉज दिस इज वन टाइम लर्निंग गाइस. इसके बाद आप जब पढ़ोगे ना, वो और एडवांस लर्निंग रहेगी. सो इफ यू आर गुड एट बेसिक्स, सो यू विल नॉट फाइंड एनी डिफिकल्टी, राइट? तो मेरा मेन ऑब्जेक्टिव क्या है कि आपको बेसिक से समझा देना हर चीज. ठीक है, सो नाउ वी विल टॉक अबाउट एलिमेंट्री प्रॉपर्टीज ऑफ एक्सपेक्टेशन. मतलब कुछ इंपॉर्टेंट प्रॉपर्टीज होती हैं, जैसे कि इफ रैंडम वेरिएबल्स they are positive, all the values that the random will take is positive, okay? And the probability is definitely a positive quantity only, right? You can say non-negative. So your expectations shall also be non-negative, right? I mean, expectations should not be negative, okay? And yeah, so I think we will catch up in the next session only, right? Regarding properties and all those things. So please take this lecture, okay? I don't want to make all the lecture more than 1 hour, so this suffices for today. We'll meet in the next session. We are going to talk about expected value rule, okay? And we will take some examples as well, और बहुत सारी चीजें डिस्कस करना है, मेनली प्रॉपर्टीज ऑफ एक्सपेक्टेशन. ठीक है, थैंक यू.